Hello, my students, and welcome back to class. It looks like I will only be able to make one video a week. These take a lot of time, and so this is about all I'm going to be able to do, but I think it's okay. Having talked to Asiana Baksh and talked to Bujidma Baksh, I think it'll all be okay if we only do one class a week. So here we go. We're going to work on the Wilson cycle starting today. We'll see how far we get through the Wilson cycle. Try to just keep it to an hour and a half. And all right, so your quizzes, you did pretty well. I'm going to make a second video at some point really quick and talk through what I want you to do. I want you to redo the videos, at least one of them. I want you to redo the convection cycle in the mantle, the plate tectonics one, because it's a really important idea. You're close, you're starting to understand. I've decided the way I'm going to teach this class is to comprehension. I'm going to just see how far you can get in understanding the concepts. It's a way of teaching that I've wanted to do for a while, so you guys will be my guinea pigs. All right, so what are our objectives today? I'm going to review the convection currents in the mantle. I'll review plate tectonics one more time. I'm okay with redoing some things until you understand. So don't feel bad. This is an idea that my students have always struggled with, but you're going to get it because we're going to repeat it so many times that you're eventually going to be able to do the whole thing and have confidence that you understand it, okay? So we'll do that. We're also going to get through at least 3, probably 6 of the Wilson cycle stages today. And as we go through them, I want you to be able to, when you do your videos, you need to be able to describe what's happening in each stage. So some of them, barely anything's happening. Some of them will have a very short description. Some of them will have a long description. Some of them will need some drawing. You have a drawing of the Wilson cycle that I've sent to you. If you don't have that out yet, or if you haven't printed that yet, please pause the video and go get that printed. Actually, I'm going to show you what it looks like. Please go print this page. You're going to need it to look at through what we're talking through. Write notes on it. You can use it for answering the questions later. I want you to be able to look at this and understand it. This is what we're doing. The whole class is going to base, almost the whole class is going to base around this Wilson cycle. All right. So let's go back to the PowerPoint. And all right. So I want you to be able to describe what happens in each cycle, each stage. I want you to give an example of a real-world location, and there is a real-world location for each of these things happening on Earth. Some of them are really easy to see. There's one that's a little hard to see, but I want you to be able to look at a map of or a globe of the Earth and say, that's where that is happening. So give examples, one or more examples of each location. And then right now we're only focusing on igneous rocks. Hopefully I have updated the notes at this point. While I'm making the video, I know my notes are not updated, but we're only focusing on igneous rocks this time. If we have time, we'll go back and go through sedimentary, and then it would be a miracle if we got to metamorphic. We'll see what happens. So tell me if there's igneous rocks that are being made in that stage and why. Explain why they're being made in that stage or why not. Don't just say they're not being made. Tell me why you know they're not being made in that stage. What is happening or not happening so igneous rocks would not be made. And I actually got an answer back from one of you already on this, and you understood. So I need an email from 2 of the rest of you, from Ina and from Tomo. Go ahead and explain to me why ocean basins are low and continents are high. And yeah, we'll get to that in this lecture, but good Good job, Akla. You got it. You understood. The right guess. All right, we did all of this last time. So chemical strata of the Earth. Again, we're looking at the chemistry, the density of the elements. The lighter ones are going to go up, and the denser ones are going to go down. I'm just going to swing through these real quick. Our mechanical layers we're talking about physical characteristics, how they if they're solids or liquids, or a plastic, which can act like both, right? So these form because of differences of pressure and temperature. Just running through this really fast. 3 types of rock. What are the 3 types of rock? Tell each other. Ready? Okay. Igneous, metamorphic, sedimentary, and metamorphic. And we are mostly focusing on igneous rocks. So I want to look at the definition of an igneous rock again today, because we're going to talk about where are these igneous rocks forming. They form from melted rock that has become solidified. So melted rock itself is not an igneous rock. It's a liquid. A liquid cannot be a rock because rocks are solid. So some sort of rock melts and becomes magma. Magma is melted rock. And this process always starts under the Earth's surface. It doesn't start at Earth's surface. And most igneous rocks form under the ground. We see the ones that are made by volcanoes, but most igneous rocks don't form from volcanoes. Most igneous rocks form deep in the earth. All right, again, Egan, I know in my last set of slides, you couldn't see a lot. The edges were cut off, so I think I've got the proportions right on this now. But Egan means fire, so think hot and melted. It starts because of hot and melted rock. It isn't a melted rock, but it starts because the rock was melted. All right, I'm going to just zoom through this. I would normally make you guys go through this again, but we've got a lot to get through, and so we're just going to move along. We're looking at this portion over here of the igneous rocks part of the cycle. Right, so we're going to mostly focus on igneous rocks and the minerals that make them and the processes that make them. So there's going to be a point where we're going to focus on minerals. When we get to minerals, we're talking about chemistry mostly. Processes, this is what's happening in the earth, what is happening with plate tectonics that's causing these rocks to be created. Right. Still on review, rocks are created because of plate tectonic movement. They're destroyed because of plate tectonic movement. They can be changed because of plate tectonic movement. But plate tectonics is what's driving everything. And again, plate tectonics is the theory that explains why and how pieces of the lithosphere, the surface of the earth, are moving around and interacting with each other. And you couldn't see this whole thing last time, so hopefully you can see the whole thing this time. Tect. It's a great root. It's a wonderful root, meaning to build. And so when you hear plate tectonics, and we're going to have other words if we get to it, with tecto in it in this class. So always think build. For plate tectonics, think building new continents, new oceans, and new rocks. Oceans being the rock underneath the ocean, not the water. All right, we're getting close to where we can just start, but I really want to focus on this plate tectonics thing here. Plate tectonics explains how continents and oceans move. This is still all review from last week. How Earth's rocks, continents, and oceans are made, changed, and destroyed. All right. So that's what plate tectonics explains. And I think you guys answered that. I think I had a question on that. I need to go back and look at my questions and your answers again. All right, and again, we're looking at chemistry. And so these names, felsic, intermediate, mafic, ultramafic. Oh, I still didn't fix that. Ultramafic needs to be there. Mafic needs to be there. These are names of the types of chemistries or compositions of the igneous rocks. Oh, there we go. We're going to see that one again in a little bit. Let's skip past this. Whoops. Where am I? Oh, that one's fixed. This again is just the reminder that the mechanical layers correspond to or are can be matched up with the chemical layers of the Earth. And that the most important thing for us to know is that the lithosphere, the mechanical layer of the lithosphere, has part of the chemical mantle and part of the chemical crust, be it oceanic crust or continental crust. Bailey, what you doing? What you doing, bud? Watching for my dog, keeping him out of trouble. Come here, Bailey. You want to come say hi to my class? Come here. Come here. Come here. Oh, you don't be a stinker. Come here. Oh. He doesn't want to come up. Oh, well. Okay. Oh, maybe he does. Here he is. There's my dog. Say hi, Bailey. He might sit with me for a little bit. He's a little lonely. All right, we'll see if that gets distracting or not. Okay, so here we go. This is what I really, really want you to memorize. This is that you won't hear me say I want you to memorize very often because y'all memorize really well, but this is something that's important to memorize. So the continental crust is the continental crust. That's the crust that we live on, the rock where we live, is made out of felsic and intermediate chemistry. All right, the composition are felsic and intermediate. So when you hear continental crust, we're talking about the rock that's not under the ocean, the rock that we live on, and the chemistry is felsic and intermediate. When we talk about the ocean crust, you getting down? The ocean crust is mafic in composition, so a little different there. And then the mantle rocks underneath both the ocean and continental crust are ultramafic in composition. And what's really important to remember in this diagram is that as we go towards felsic and intermediate, the density is going to be low. The further we go that direction, the lower the density. The further we go this direction, the higher the density. Get that piece in your head, and it'll help you answer a lot of questions later on. All right, I'm going to skip through this. We've done this already. If you have any questions on this, go ahead and look back at the last video, right? Skipping through. I do want to get to, sorry, I should have just taken this out. So tectonic plates are made out of lithosphere, and the lithosphere again has the mantle in it, and it has continental crust and oceanic crust in it. So the solid tectonic plates float on top of the asthenosphere. The asthenosphere is also chemically mantle, but the asthenosphere is more of a plastic liquid than it is a solid. So we've got plastic down here. That's hard to see over the pink. And we've got solid up here, right? And we've got felsic and intermediate composition, which again, remember that means low density. Low density, it doesn't mean low density rocks, but they are low density. Oceanic crust, which is mafic, and its density is kind of in the middle, right? Its density is not low, not high, it's medium. And then the ultramafic mantle rocks, and this has high density. All right, there we go. This is where we need to really focus, right here. I want you to understand this process. I think it will help you if you understand this process. So we're going to look at this animation a couple times here. We've got heat coming out of the core, which you guys got that part just fine. And the heat is going to enter into the rock. There's going to be a bunch of rocks out here. And it's going to decrease the density because it's expanding. All right, I'm going to go back. Come on. So the heat goes into the rock takes the heat in, becomes expanded and the density lowers so it rises. And then I want you to follow this path. This was where you guys kind of got off in your explanation. You were just drawing arrows anywhere. I want you to follow that circle that it makes. It goes up, and then it doesn't just go anywhere. It goes underneath. This is the mantle, and up here will be the crust, right? And it's made out of lithosphere. It's the crust, and so we've got the lithosphere with the asthenosphere up here. So we've got asthenosphere and lithosphere. And this is making a complete circle. It's going around and around again and around again, just like water in a pot goes around and around if you watch the rice. So follow that path. It goes up, and then it pushes underneath the asthenosphere and the lithosphere, and it drags it along. So if I've got something pushing under here, just by friction, I'm going to pull along. So this is the mantle that's moving in a circle like this, and it's going to pull along whatever's on top of it by friction. It's going to move. And then at some point it will sink, and it probably or possibly will take part of the ocean crust down with it. It doesn't always, but in our lessons today, we're going to see where it takes down the ocean crust. And then it will sink because it's lost its heat energy. The density will increase, the volume will decrease, and it will sink. I think I was saying something wrong over here. Density decreases over here. Density increases as it's sinking, or it sinks because the density increases. Let's try that again. Read up on it. I am proud of you. You guys keep reading outside of what I've given you. You keep learning outside of just what I've given you, and it's helping you. So go ahead and do that. But the next time you go through this, I want you to make the circle. Please make the entire convection circle. All right? And add in what's happening with heat. Where's the heat coming in? Where's the heat going out? It's going out when we get up here, right? We're losing heat up here. Where's the heat? What's happening with density? When's density decreasing? When's density increasing? What's happening with friction and dragging along the asthenosphere and lithosphere up here, right? So try that again. We're going to just keep walking through it, and I'll see if I can help you as we go. Great. All right. So convection cells are driving plate tectonics. And so here's the walk through one more time, all right? Heat moves out of the core, and it makes the mantle hot. So we've got a mantle rock here. The mantle rock, because of heat, expands. It gets bigger. Because it expands, its density is going down, and it's going to rise up. So now our mantle rock is here. Here the heat is escaping into the asthenosphere. It's going to cause melting. It's going to cause volcanoes to form. It's going to cause all sorts of things at this point. But it won't just stay right there, because there's more hot rock coming up underneath it. So it's got to go somewhere. Where's it going to go? It's going to flow. So our rock's going to move this way. It's going to flow underneath the asthenosphere and lithosphere and pull it along, pull the lithosphere and asthenosphere along by friction. And eventually it's going to get over here where it's getting cool. It's lost all of its heat energy up into it's lost part of its heat energy up into the crust and up into the asthenosphere. That means that it's going to cool, and its size will decrease. It's going to decrease in volume, which will increase its density. So density is going to increase over here, and it's going to sink. And when it gets down here again, it'll pick up heat from the core and make that entire circle again. All right, so go ahead and try. Do that exact same quiz one more time. See if you can get all of the pieces in there, and I'm looking forward to it. I'm going to be grading y'all on just completion. Just do it show me that you understand, and we're going to get there. Hold on a second. Oh, Bailey, come here. I don't think she's going to appreciate you chewing on her shells. Let's play with your toy, huh? Let's do this. I have to keep the dog entertained while I'm teaching you. Go get it. Where'd it go? Go find it. All right, 3 types of boundaries. You guys got this just fine. We've got divergent, going apart, convergent, going together, 3 kinds, ocean to ocean crust, ocean to continental crust, and continental to continental crust. Transform. We really don't care about transform in this class because it doesn't make anything but metamorphic rocks, and I don't think we'll get that far. Okay, so we've got, again, divergent boundary happening here where we've got the convection cells moving things this way, and then we've got convergent happening over here. We're going to see this particular location today. We'll see this today. We also have convergent over here, where the ocean crust is going under the continental crust. All right, these are all the different plates. I'm going to pull this up at least one other time so you can see where specific things are happening. I probably should come back to it a few times, actually. We'll see. I am sorry. I apologize. I am very distracted today, and it's partially because I'm running out of time to make all of this. So if I'm going too fast, I am sorry. But a lot of this so far is review. You guys did just fine on this. The only thing that I wanted to correct on the video that you made for the 6 tectonic regimes was that a passive, you got passive, no movement, no heat, meaning no movement. Active, it means that there's heat and therefore there can be movement. It doesn't mean necessarily that we'll have volcanoes, but we would expect to find volcanoes. What else would we expect to find? If we have movement, rock moving against rock, what else do we expect to find happening when rock, especially if rock goes underneath rock? We expect melting and volcanoes, but we also expect earthquakes, right? The Earth's going to shake. There's going to be friction and release, and that will cause an earthquake. Great. All right, so no passive regime happened because no heat's being added. If there's no heat, there will be no movement. Active regimes, heat is being added, therefore we will have movement. There is one stage where we don't have heat added, but there will be movement. And it's because of heat in a different location driving that movement. But almost always heat and movement are connected. And you can almost always see the connection. All right, back to the Wilson cycle. 3D model, it's going to show us what's going on as plates interact with each other. Bailey, stop it. Here we are. Hopefully where my dog will not get in trouble. Have you ever owned a dog? Did it get in trouble? I'm going to be throwing this once in a while because he's got a lot of energy. All right, so Wilson cycle. Let's get back to it. The Wilson cycle, it's a model. Yeah, so it's a 3-dimensional model where we can look at the map. We're going to look at the globe and see how plates are moving around one another. Are they moving apart? Are they moving together? Are they moving under each other? And then we're going to look at a cross section. So we're going to look at it this way, where we look down at it, right? We're looking down at it, and we can see. Let's see, we've got a plate that's moving under another plate. So you can see that from the top. But I also want you to see what it looks like from the side, where one plate's going under another, or plates are being how do I do that? Moving apart this way. And again, rocks are being created, transformed, and destroyed through this process. I think I showed this to you last time, but we're going to look at this. We're going to look at this a couple different times. So here's a video showing what's going on. So we start, I'm going to pause this. We start with a continent. This is stage A. This is stage A in the Wilson cycle, where we just have a continent next to the ocean. There's ocean all around this continent. And then heat starts coming up from underneath and starts to rift the continent. This is stage B, where the continent starts to come apart because we've got convection in two sides. We don't have arrows for that. This is stage C, where we're creating ocean crust. That black being ocean crust, the gray on the sides are continental crust. This is stage, on the right you can see stage D, where it's just nothing's happening, the passive margin. On the left we've got stage E, where ocean crust, this is actually stage FG, might be G over here. So we skipped a couple stages. We're going to look at this though, so we'll see what happens. But two of the stages look like two other stages, so we'll see how that works. Then we've got two continents hitting each other and creating big mountains, pushing each other up like that. All right, so we're going to see how all that works, especially through the cross sections, how each of those work. Right. Oh, get rid of that. That's really interesting. Ah, cool. I didn't know I could do that. All right, let's look into it. So each step of the Wilson cycle shows how the plates move over geologic time. We start here at stage A, and it's going to change and become stage B, and so on. Want us to be really clear what layers we're looking at inside the Earth. So in your mind, as I go through these, I want you to say out or say to each other, is this a chemical layer or a mechanical layer? Okay, so first of all, we've got the continental crust. All right, so all of this is continental crust. Sometimes the continental crust has mountains, sometimes it's flat on top, but it's a lot thicker than the oceanic crust. Is the continental crust mechanical or chemical? Which one is it? Continental crust, is it mechanical or chemical? When we talk about crust, every time we see the word crust, we're talking about chemical. So it's a chemical layer. All right, so that should make this one really easy. This right here, this thin layer, is oceanic crust. Is it mechanical or chemical? It is chemical, yes. Hopefully you got that. All right, so the continental crust, again, what chemistries does it have? What compositions does it have? It has felsic composition and intermediate composition. An ocean crust, what chemistry does it have? It has mafic composition. Great. All right, the mantle. The mantle itself, when we just say mantle, are we talking about chemistry or mechanical? Chemical or mechanical layer? Chemical layer. What is the chemistry of the mantle? What is the chemical composition of the mantle? It's like mafic. It's ultramafic. Oh, I wish I could hear your answers. I bet you're getting it right. All right. The lithosphere. All right, so this should be a hint. The lithosphere starts up inside of the continental and oceanic crust, and it goes down to part of the mantle. So we're talking about a chemical layer or a mechanical layer here. This is a mechanical layer. And is it a solid or a liquid, really, is what I'm looking for. This one's a solid. It's what we stand on Earth. Underneath that, we have the asthenosphere. Is the asthenosphere a solid or a liquid? It's a plastic. It acts like a liquid. It acts like a liquid. Ooh, that's the edge of my liquid. Hopefully you can see all that. Great. Keep these pieces in mind. Here we go. So we're going to start off with the first stage of the Wilson cycle is very simple. It's a very simple model. In this stage, all we have is continental crust. In the middle, it's a lot thicker. It goes up higher and down lower than oceanic crust. We've got continental crust over here and over here, and it goes on for a long time. It doesn't just stop there. It keeps going that direction. Keeps going that direction for a long distance. This is the oceanic crust. Underneath the oceanic crust and the continental crust is what chemical layer? What chemical layer is underneath these? The mantle. The mantle chemical layer of the Earth, right? So we've got felsic and intermediate. We've got mafic, and we've got ultramafic. See how these line up with the nice pretty drawing? There's the oceanic crust and the oceanic crust. The continental crust and the continental crust. You can see again, the continental crust is a lot thicker than the oceanic crust. And we'll find out why. It has to do with chemistry. We'll find out later why. And underneath all of that is the mantle. Here we go. Sometimes nice to see the pretty drawing so that your brain can go, oh, okay. Oh, and then this line up here, whenever you see this line up here, that's just the line showing you the top of the ocean water. So this is all water. This is rock. The black is rock, and between the black and the little line is water. I want you to understand this drawing, because if you understand this drawing, it'll make the rest of the drawings a little easier. All right, so stage A, what is it? It is a theoretical beginning, and actually the entire Wilson cycle is theoretical because we can't watch the whole thing happening, but we've got evidence of it all over the planet. Stage A is a theoretical beginning. It begins with a big continent. In reality, we actually probably started with all ocean crust. We probably started later in the stages and then made some island arcs, and the island arcs all stuck to each other and made a continent, okay? Rather than going from there, we're going to just start with a continent. Stage A is a possible beginning. A continent, it's completely flat on the top. We call it penaplaned. We don't care about that until we get to sedimentary rocks. But a flat continent with ocean crust all the way around it. The continental crust has low density because it's felsic and intermediate composition, and the ocean crust has high density because it's mafic composition. So the continental crust stays up higher on the mantle. Both of these are floating on the mantle below it. The continental crust floats up higher. The oceanic crust floats lower on top of the mantle because of density. This is a passive regime. What does passive mean again? It means there's no heat being added, so no movement, right? Passive regime. It's cold here today. It does get cold in Texas occasionally, though you wouldn't think it's cold. All right. So we've got felsic and intermediate continental crust connected to mafic oceanic crust, all sitting on top of ultramafic mantle. Are igneous rocks being formed here? I wish that no hadn't come up right away. No, why are igneous rocks not being formed in stage A? Why are we not getting igneous rocks? Well, how do we form igneous rocks? How are igneous rocks formed? By melting, and you cannot have melting if there's no heat. So this is a passive regime. It's a passive regime, so there's not going to be any heat added, so no igneous rocks can be formed. No melting, no igneous rocks. A good example of this location, the best example that I can give you is Australia, because it's one big continent with ocean crust around it with barely any tectonic activity happening. Canada in northern North America and parts of Siberia in Russia are also examples of stable cratons. Stable craton, I didn't talk about this name yet, did I? Stage A is called stable craton. Stable means nothing's happening, nothing's moving. Craton means a continent. It's a big, solid, not moving piece of rock. Nothing's happening to it. It's just thick rock that's not going anywhere. These are what we would call geologically quiet continents. They have almost no tectonic activity. What does tectonic mean again? Nothing is moving, nothing's happening to build anything. So there's no volcanoes, there's no earthquakes. Now, if you go look up, does Australia have earthquakes? It does, but it's for other reasons. All right, so there's Australia for you. That's the best example I can give you of stage A, the whole thing. It's one continent surrounded by ocean crust. And this is all on one big plate. So all of this out here is the plate. The movement's happening out of the boundaries of this plate, but it's not happening on the continent or where the ocean touches the continent. So stable, quiet, peaceful, where you want to live, where nothing geologic ever happens. Majorly. There we go. Stable craton. All right, so that's stage A. Nothing's happening. Just continent attached to ocean crust that keeps going a really long distance with some ocean water there on the sides. Continent that's a lot thicker than the ocean crust with mantle underneath. Just floating around on the mantle. Really quiet. All right, stage B, all of a sudden we have arrows. If I have an arrow, what does this mean? What's going on here? Is it passive or is it active? It's got to be active, right? If we've got arrows, there's movement. So that movement is being fueled by some sort of source of heat, right? Where's that heat? Well, maybe you can see here we've got something's going on right here, right? And oh, what could that possibly be right there? We've got something happening, right? So this is an active regime. We have heat, and we have movement. I'm going to go back and forth here so you can see again what's what. Oh, so we've got the ocean crust, and the ocean crust here. We've got the continental crust, and the continental crust here. We've got the mantle, and the mantle here. Only in this drawing down here, there's no movement going on. In stage B, there is movement going on. All right. Why are these? Oh, so I've got two arrows, right? And they're moving apart from each other, away from one another. So movement apart. Why are the plates moving apart? What is happening? What's causing this to happen? It's going to be convection in the mantle. So we've got heated mantle rocks coming up and going one direction. Heated mantle rocks coming up and going a different direction. And they're pulling apart, and the continent's on the top, and it's getting pulled and stretched apart. Like imagine soft candy that you can pull. Taffy is what we call it in English. Pull, so start with a big piece and you pull on it and it gets thinner and thinner and then it'll break in the middle, right? So we've got convection happening that's pulling apart the continent. This is what's causing the plate tectonics, the movement above. So we start with stage A, and then we've got convection happening underneath that's pulling apart. It's adding heat, right? So we've got heat that's being transferred out of the mantle into the asthenosphere. And some things are going to happen here. We're going to get some partial melting of the asthenosphere. So now we've got magma, melted rock, and that magma is going to go up. We're going to get some volcanoes. And we're going to get movement. We're going to get earthquakes along these rifts. Lots of movement, lots of heat added. All right, so remember, convection is just a means of moving heat out of the earth. We're moving heat from the core of the earth through the mantle up into the asthenosphere and the lithosphere, the crust of the Earth. The convection in the mantle is creating a divergent boundary. Diverge means go apart. To go apart, diverge. Divergent boundary in the crust. The mantle transfers heat by conduction, so the mantle is convecting, and then the heat in the mantle is touching the crust and conducting that heat into the asthenosphere and into the lithosphere. The asthenosphere has enough heat now that that rock, even though it's been acting like a liquid, it's really a plasticky solid, it partially melts, partly melts. That means, we'll get to it when we get to the minerals. Some of the minerals melt easier than others, so the easy to melt minerals are the ones that are melting. It partly melts. All right, so are we going to get igneous rocks? Yes, we're getting igneous rocks, yes. All right, why do we get igneous rocks? Where are they coming from? We have some melted rock, right? So the heat transfers from the hot mantle to the asthenosphere. It partly melts those rocks, and when rock melts, it makes magma. The melted rock is called magma. That magma will stay there and then cool, or it will move and then cool somewhere else. When it cools, it crystallizes, it makes new igneous rocks from solidified, cooled magma. All right, so here we've got some more animations going on. We've got heat going up through the convection cycles. Heat's going to hit this is the asthenosphere here. And this rock is going to partly melt. And it's going to get stored inside of the continental crust, or actually we're going to get secondary melting. We'll get to that later. And then that melt will go up and make volcanoes. And we're going to have igneous rocks formed in each of these locations. We're going to get new igneous rocks definitely up where we've got the volcano, but also where the magma is moving up, down here, and even down here in the asthenosphere, we're going to get some new igneous rocks. All right. Where on Earth is stage B happening? The best example that I can give you is the African Rift in East Africa. But another location, which is really near to home, is Lake Baikal in Siberia. So this is Africa, and we've got rifting happening all in here. There's rifting happening. And this is what's happening. The heat's coming up. This is a cross-section in Africa. And if you zoom in on this area, you'll see there are plenty of volcanoes, lots of volcanoes that are forming. This is called a triple junction. Usually when plate tectonics starts, there's going to be 3 branches of rifting. Rifting doesn't just happen in one straight line because the Earth isn't flat. If the Earth was flat, it would probably rift in a line. But because the Earth is a ball, when you get a crack here, you're going to get a crack here and a crack here. So you're going to get 3 cracks. Or on this picture, you're going to get 3 rifts. So it's called a triple junction, is where 3 things, or where things come together. So in this case, it's a triple or 3-part junction. You can see where it's already moved apart. Africa has moved apart from the Arabian Plate, and it's still moving apart. The eastern part of Africa will someday separate from the rest of Africa. One more picture showing that. This is where the triple junction is. All right, and Lake Baikal is actually a similar scenario, or maybe I should say it was. Sometimes geologic activity starts somewhere and it doesn't continue. So at one time, there was a line of heat coming up underneath Lake Baikal, and there was no lake there. It was just continent. And then we started getting convection pulling apart Asia, pulling apart northern Asia. It would have pulled apart Mongolia, and it's still moving a little bit, but not very much at all. The heat is turned off, or turning off, underneath Lake Baikal. So this is stopping, but Lake Baikal was opening. It's the reason why Lake Baikal is such a deep lake, is because it's not just normal continental crust underneath. It's oceanic crust that's down inside of this rift. Thankfully it stopped. Maybe thankfully, I don't know. Would you like Mongolia to be next to the ocean? That would be interesting. All right, so that's stage B. So the locations again are Africa, and you can say Lake Baikal. It's a real location, even though it's not going to finish. It dropped out of continental rifting. So stage B, I should be talking about these names at the beginning. Continent, the continent is rifting or being pulled apart into two pieces or more. All right, stage C, we've got that convection continuing. And we're going to pull the continent apart even more and make ocean crust right in here. So when we talk about stage C, we're really talking about what's happening right here. I think on the diagram that I'm sending y'all. Oh, where did it go? Open. Oh, nope, this one doesn't have the circles. I might send you one with circles also. But in stage C, we care mostly about what's happening inside of this big circle. We don't care about the rest of the continent. All right, so in stage C, what's what? Oops. Stage C, we've got ocean crust, right? Ocean crust is over here. But there's ocean crust here too. Whoa, we've got new ocean crust, which is the point of stage C. We've got continental crust. And we've got mantle. All right, so ocean crust, there's ocean crust over here too, but we don't care about it. We really just care about the ocean crust that's being formed right here. So how does that happen? All right, this is the animation that took me, no, this is not the longest animation, but it's a, no, this is the easy animation. So we've got convection that's happening, pulling apart the continent. We're going to continue to pull apart, and we get that partial melting that's happening here. It's going to partially melt the mantle and create ocean crust. The magma that comes up, it will come up and it will become solid rock, and then this will move even further apart, and we'll get more rock put in here, continuing. It'll just become longer and longer and longer piece of ocean crust. So what's happening here? Convection is continuing to push apart the divergent boundary. Again, diverge means to move away. Opening it up more and more, so it's becoming more and more open, or the continental pieces are moving further apart, so we're getting a larger space for ocean in between them. We're getting more and more new igneous rocks. I'm very sad. It's not letting me do my questions and answers. I thought I'd fixed all of that. That's all right. So it's making more and more new rock. It's going to make ocean crust. Specifically, the type of rock is making ocean crust. Pretend you didn't see it. What type of chemistry does ocean crust have? Yes, you see it right there. Ocean crust has mafic chemistry. So this process is specifically making mafic igneous chemical rocks. All right, so why are ocean basins low and why are continents high? Why is continental rock stay up high and ocean rock stay down low so that we can get a layer of ocean water over it? It's not because water pushes down. Water is very low density. It doesn't have a lot of, it's got enough pressure to kill us if we get under it, but it doesn't have enough pressure to push rock down. It can't do that. What's causing it to go down? All right, so what is the chemistry of the ocean crust? The chemistry of the ocean crust is mafic. What's the chemistry of the continental crust? The continental crust chemistry is felsic and intermediate, so this is what we're dealing with here. What's the density of the ocean crust? Is it high or low? Is it heavy or is it light? Does it, if you pick a piece of ocean crust up, is it going to feel heavier or is it going to feel lighter? It's high density, so it will feel heavy. So ocean crust has higher density minerals compared to continental crust, which has lower density minerals. There we go. So this ocean crust has high density and it stays down below the level of the continent. But why does the continental crust sink so far down if it's got low density? It's a different chemistry thing. We'll get to it. Examples of stage C. So again, stage C is only focusing on what's happening right here. And really, what's happening right here. This is the main point of stage C, is what's happening when this melts and goes up and makes new rock right there. Examples of stage C. The best example I can give you is the Mid-Atlantic Ridge. It's when you look in at maps of the ocean. Actually, I'm going to do this. I've been meaning to open this up. Oh, where are you? Education. Nope. We'll just do it this way. Google Earth. All right, so if I look at the ocean, I can't draw on this, so we're just gonna have to look. When I look at, this is Africa over here, this is North and South America, and this is the Atlantic Ocean in between, and you can see that line that goes down the entirety of, I don't know if you can see it this way. Ooh, I don't know if that'll even show up though, probably not. All right, so you can see this line going down the middle of the ocean, and that's where magma's coming up. I don't know as far as it'll let me in, but that line there, magma's coming up from underneath and filling in a gap and pushing and making new rock as the continents, as tectonic activity, as the convection cells pull apart this rift. Divergence happening. I wish I could mark on there. That would be really nice. The Atlantic Ridge is the best example. That line. We've got movement like that. There's more of it here. More of it here. And right here. So new igneous rock is being created all along this line. How fast is this happening? This is an interesting question. How fast does this move? Is it really fast? Is it slow? Do you see yourself? My dog is like, what is this? In my computer. This moves, this moves apart at the rate of about 2 centimeters per year. Very slow. Do you know what else moves at 2 centimeters per year? Your fingernails. They grow about 2 centimeters every year. So that's not very much, is it, for the entire planet? But it's enough to make volcanoes and new rock and those occasional earthquakes out there, and it's enough to push apart the continents very slowly. All right, this, okay, let me see, I'll finish off with stage C then. Lake Baikal is a divergent boundary that transitioned from stage B to stage C, kind of. It never connected to the ocean, so it's not considered oceanic crust, but it's made of oceanic crust. It's made of mafic rocks. When the teacher tells you the answer before she asks the question. What kind of rock is at the bottom of Lake Baikal? Mafic, you're right. Oh, where did that word go? What composition? When the teacher gives you the answer before she asks you the question. What kind of rock should be at the bottom of Lake Baikal? Not composition. I didn't ask composition. Did I ask you what type? Igneous. Right. We should have igneous rocks, which we do. We have igneous rocks at the bottom of Lake Baikal. What chemistry are those igneous rocks? Yes, mafic. All right. Apparently, I need a break, so you really need a break. All right. So go ahead and stand up, stretch, pause the video, shake it out like my dog. Look at the cuteness. The cuteness of the ears. There's the dog. Take a break. Move your bodies. Don't just sit there. Stretch so that you can think. All right. All right. You ready to go? Here we go. Stage D. Stage D is really simple. Full divergent margin. Or what do we mean by this? Full divergent margin. Divergent means that something has moved away from something else. It's an adjective describing something. So we have diverged. This area has diverged. It's moved away from the other piece of continental crust that was on the other side. Margin means we're on the edge. So this is the edge of the continent. You might notice that we've got a different pattern going on here. Full means we're completely moved away from the other continent. Completely, full, moved away, divergent from the other continent, and we're looking at the edge of the continent. We don't care what's happening over there. We just care what's happening inside of this circle. All right, so how does this happen? We get convection happening, and it's continuing to push and push and push, make new and new rock here until this continent is very far away from the other continent on the other side. So question. So the continent is pushed farther and farther away from the spreading center. Stage D is only focused on the edge of the continent over here, this side. Is heat being added inside of stage D? Is heat being added inside of this red circle? Can you see anywhere heat is being added? We've got convection continuing this direction, but do we have heat being, do you see anything to mark heat being added here? This is all sedimentary rock in here, so this has nothing to do with heat. This is all solid igneous rock, so this has nothing to do with heat. It just exists. The answer to this question is no. There's no heat being added inside of stage D. Is this area passive or active? Is it, look, oops, I'm thinking of this way. Is this area passive or active? Do we have heat going on inside of it? No. Do we have movement going on inside of the red circle? No. This area is therefore passive. All right. Why is stage D passive? Teacher gave you the answer already. No heat being added, no movement inside of stage D. Passive, peaceful, nothing happening geologically of any great significance. At least nothing of movement. Are igneous rocks formed in stage D? We have igneous rocks there, but are new igneous rocks being made in stage D? No. No. Why not? Why are no igneous rocks being formed in stage D? I'm sure you've got it. There is no heat being added in stage D. So we can't melt any rocks here, therefore we're not going to get any new igneous rocks. Very simple. Examples of stage D. The east coast of North and South America, the west coast of Europe and Africa, around India, all the way around Australia. Lots of good examples. These are areas that don't have current tectonic activity. India is a great example of this. It's just super quiet all the way around. Nothing's happening here. Just rock, just continental rock, and oceanic, the continental crust and oceanic crust hanging out. Just sitting there. Very similar in that way to stage A, with nothing happening. Great. Moving on. Stage E. All right, this is where things get really interesting. This animation took me hours and hours to create, but you are worth hours of investment. So here you go. This is how this works. Stage E, we only care what's happening inside the red circle. Okay? Don't care what's happening over here. We don't care what's happening over here. The main point of what's happening is in the red circle. But why is it happening? We need to look at the whole picture. So we're going to look at the whole picture. We're going to start with stage D, where we've got stage, actually what we've got here is two things. We've got stage C, and here we've got stage D. All right, I wonder if I can get rid of those marks. Yes, I can. Good, because I need to. All right, so you can see what's going on. Awesome. Paid for it. It's working now. All right, so stage C over here, stage D here. Got a bunch of oceanic crust that's been formed. Let me erase that again. All right, what's going to happen? Let's watch. What's going to happen right here? Think about it for a second. Talk to each other. What's going to happen under stage C? It's going to continue. It's going to just keep going. We're going to continue to have convection come up. All right. What's going to happen with this oceanic crust in here? What's going to happen here? Think about if convection continues, what's going to happen with this crust? Is it going to stay the way it is? Is it going to become smaller? Is it going to become larger? It's going to get larger. It's going to keep growing. Let's watch that happen. I think. Oh, please work. This is super important. Oh, it's so confused. Oh, it's frozen. No. All right, let's try again. We'll load from that page. This is super important. There we go. Convection is continuing and it's pushing and we get a whole bunch of ocean crust, all right? So think in your head, Earth is round. It's this big ball. And if I continue to add, like create new crust here, what's going to happen with the rest of the planet? Something has to happen. If I'm creating new crust here, something else has to, we're going to keep moving things, right? But eventually everything's going to come back over here. It's not an infinite amount of space, right? So something else has to happen. So eventually we actually end up with another convection current coming from the other side. And I'm going to go back and forth between those. All right, so another convection current is going to move from this side, and it's going to oppose this convection current, all right? So that convection current can't go forever. Eventually, it's going to run into another one. All right, so I've got a convection current coming this way, and I've got a convection current coming this way, and eventually they're going to hit, right? All right, and when that happens, oops. When that happens, uh-oh, this keeps freezing. This is a lot of animation. My little iPad can't handle it all. When that convection current comes from the other side, it's going to drag the continent back the other direction, drag the ocean plate back the other direction, and we're going to get stress that happens on the ocean crust, and it can't just stay, it can't just stay the way it is. So it's going to end up breaking, and one piece of the ocean crust is going to subduct, go under the other piece of ocean crust. So this piece, they were connected to each other. They were connected, and it's pushing and pushing and pushing, and then it fails, and it goes underneath, and it subducts. And when that happens, we're going to push this ocean crust down into what layer? What chemical layer is under the ocean crust? Oh, let's get the mantle, right? And the temperature down here is high. We're going to heat up this ocean crust, and we're going to actually start to melt it. And it's going to come up, melted, and come through the ocean crust here and create a volcano. There we go. Those convection currents, you see, they didn't continue to be straight at each other. They can't continue to just oppose each other like that. Something has to happen there, so they eventually change direction and start going under too. And that convection current that's going under is going to drag that ocean crust down with it. And this one's just going to start turning around and going back. They're both going back down towards the core of the Earth. Whew. Hoping that was helpful. Oops. All right, there we go. No. How do I move on? And now all I can do is draw. All right. Oh, I have to go through the whole thing again. That's all right. All right, so we end up with stage E, and this is really kind of the bounds of stage E right here. We've got the black again is ocean crust. So we've got ocean crust and ocean crust. The ocean crust went all the way to here. But when this comes through, it melts and it comes up and it starts to melt and create an island that builds up from a little tiny island all the way up to a big island. Oh, I've got another video for this, and I forgot to save it in here. I wonder if I can find it. I'll throw it in later, but it's going to show how ocean crust goes under ocean crust, and then you're going to start seeing these little volcanoes pop up in a line. Those volcanoes get bigger and bigger and end up connecting to each other to make an island. So what is this? We're going to talk through it. Now, if we've seen it, we're going to talk through it one time. Happening in stage E, we've got more and more ocean crust being created as spreading center. Stage C. The Earth is round, so we can't just keep making more ocean crust forever. It's got to go somewhere. So we've got more and more ocean crust. It's being pushed out. What has to happen? At some point, somewhere else on the globe. So we've got ocean crust being created here. Somewhere else on the globe, the ocean crust has to break and give way. Ocean crust doesn't. One piece of the ocean crust is going to go down. It could go this way. It could go this way, but it's going to go. So part of it's going to end up underneath the other piece. When we have crust going under crust, what do we call this process? Call it subduction. So this is a subduction zone, ocean crust going underneath ocean crust. The subducted plate will be pushed down into what chemical layer again? So this is crust. What chemical layer is underneath? The mantle. Oh, going too fast, Carrie. The mantle is underneath the ocean crust, right? They have two main differences. One main difference is chemistry, which influences density. Thankfully for us, I don't know what happened. It's some other system, but the ocean crust's density is not terribly much lower than the mantle's crust. So we've got the ocean crust is a little lower in density than mantle crust, than mantle density. But the main big difference is that the deeper you go into the Earth, the higher the temperature will be. So the mantle is much hotter than the ocean crust. What will happen to the cold oceanic crust when it subducts into the hot mantle? And I'm talking very cold. The bottom of the ocean is about 1 to 2 degrees Celsius. It's right above freezing. So this cold ocean plate goes into the hot mantle. What will happen to the ocean crust? The solid ocean plate will become hotter and hotter and will melt. And what is this melted rock going to be called? What do we call melted rock? Starts with an M. Magma. We call melted rock magma. So we've got magma. Magma forming, and it makes a magma chamber. So the melted rock, the magma, magma is always going to be less dense than solid rock. So what happens to less dense things compared to high density things? Less dense things are going to go up, right? So it moves up. When the magma moves up and it hits the ocean crust, it's still lower density than that ocean crust. And so what will it do? It will make its way through the ocean crust and create. So the magma goes through the ocean crust and creates what? A volcano. All right, so here's a big question. Oh, I meant to get some pieces of paper to show this. I've got a couple journals over there. We'll use those. All right, so the ocean crust goes under ocean crust. And my question for you is, when it goes under, so let's say this is a piece of ocean crust and this is a piece of ocean crust, when it goes under, is it going to create only one volcano, or will it create more than one volcano? This is an important question. Is it just one place where heat's coming up and it's just going to make one volcano? Or is there plenty of places, lots of places for the heat to come up? All right, so I've got all of, woo! Let's see if I can hold it this way. Nope. There we go. So all this is going to be the subducted ocean crust. This is going to be the ocean crust where the water is above it. And this is the subducted, let's see if I can hold it this way where I can get a little bit more. Hard to watch myself in camera and do this. All right, so this is the subducted ocean crust. It's hot, it's melting, and it's melting along the whole edge of it, right there. Along that whole edge, right there is melting. And as it melts, it's going to send up magma in multiple places, and we're going to get multiple volcanoes in a line. Volcano, 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 all in a line that's parallel to that subduction. So the subduction is right here. This, where we can see the subduction is right here. And there'll be a line of volcanoes right here. Those volcanoes, so we've got multiple, many. The answer to that one is many volcanoes. Why will the subducted zone create many volcanoes? Because it's not subducting just one little piece. It's subducting a long piece under another long piece and coming up, and melted streams all along that line. I'm supposed to have a video here. I will copy in the video later because I think it'll take me a little while to find that video. Okay, so here's that video. Thought I'd throw it in here. And we've got oceanic crust subducting under oceanic crust, and you can see that there's melting happening there. And it's moving, that melted magma is moving up through the oceanic crust. It's gathering more and more magma. And now it's about to pop through the oceanic crust. And when it does that, first of all, there's a little underwater volcano, but soon enough it grows large enough. And there we go. We've got a volcano that's coming up through the water surface. But is it the only volcano? No, because this is a long, like a piece of, think of a piece of paper going underneath another piece of paper. More islands are going to be formed along that same subduction zone parallel to the trench, parallel to the valley that's being formed from the oceanic crust being pulled down. All right, so the line of volcanoes will become larger and larger until they connect. So I've got an island here and here and here and here, and they're getting larger and larger. And if I've got two islands that are getting larger and larger, they're eventually going to get big enough to touch each other, and I'll have a long bit of Long Island. I'm not sure why that came up. That's making me concerned. Okay, hopefully it's going to keep recording. But that also tells me I don't have very much more time. A, B, C, D, E, F. All right, so we're going to move on to stage F here in just a moment. So the plate boundaries, because the Earth is round, it doesn't actually have subduction zones that are straight lines. They're going to be rounded. There's going to be rounded lines for the subduction zones. So the long island itself will also have a rounded shape. That rounded shape is called an arc. So the line of islands becomes what we call a volcanic arc. Volcanoes in an arc shape. That's the cross section. It'll make a little sense here when I give you the example. The best example I can give you of stage E, volcanic arc mountain building. Again, I'm not telling you what it's called. Volcanic arc, we've just explained why it's called a volcanic arc. A bunch of volcanoes in an arc shape. It's making a mountain. All right, so it's making a line of mountains because of the volcanoes. The best example is Japan, but New Zealand is another example. So here's Japan. Japan is made of a bunch of volcanoes. I'm just guessing. There's more than this also. A bunch of volcanoes that were small volcanoes. This is the Pacific Ocean crust subducting under the Asian crust. And this is oceanic crust subducting under oceanic crust. It was melting underneath, so this ocean crust is subducting, and it gets hot and it melts. Makes all these volcanoes. The volcanoes get larger and larger until they connect and become one long island. And you can see Japan is not a straight line. Japan has a curve to it, an arc. New Zealand is the same way. If you look closely at New Zealand, actually we can do that really quickly. Let's go find New Zealand. All right, so there's Japan. Up there, you can see that it's an arc. There's subduction happening from the ocean crust there, and there's actually some other subduction happening on the south. And then New Zealand. Where's New Zealand? Hello, there we go. You can see the archy shape, and it's actually kind of two arcs together, but it's also made out of a string of volcanoes. This dark line that you see, anytime you see that dark line in the ocean, so you can see a dark line here, you can see a bunch of dark lines in here. If we go back up to, oh, there's a good one right there. That dark line, and this dark line up here. Anytime you see that dark line in the ocean, it means it's a subduction zone. It's a very deep place. So when ocean crust subducts, the top plate doesn't just stay flat like that. It gets dragged down, and it creates a valley in the ocean, a very deep valley. So that dark color is showing where that, right in here, where it's deep. The ocean is up above here, the water, and it's just deep in here. Actually, I'll draw that for y'all. So here's the ocean water. Oops. And here's, no, let's do something else. Oh, let's use like a dark color. There we go. All right. Ooh, that was an even better dark color. Hurry, Carrie. Just make a decision. All right, so we've got the ocean crust. We've got ocean crust here. We've got ocean crust subducting here. And this ocean crust is going to pull. It's going to grab at this point and drag that that edge down so that this part of the ocean is going to be very deep. And again, we've got this rock is melting here. It's moving the magma up. It's going to move through the ocean crust, make a little underwater volcano that's going to get larger and larger until it becomes an island now that's above the water. And there's going to be a row of those. How we doing? All right. I think we can get through stage F, so let's do it. So that was stage E. Here we are at stage F. Let's talk about the name right at the beginning. Island arc. So that's what we were just in. Stage E is an island arc, volcanic island arc. And continent, or island arc and island arc, but just to be simple, let's just say island arc and continent collision. What is a collision? It's when two things hit each other. All right, so we're going to look at how this works. We've got convection continuing, coming up over here and over here, going around. We've got this convection that's continuing this direction. This ocean crust is continuing to go underneath this ocean crust. This island is getting bigger and bigger, actually. Now I'm going to erase that real quick. We're going to watch what happens in the animation here. All right, so what happened here is the island arc itself is being pushed. We've got new ocean crust being made here, more and more and more ocean crust being made, more and more ocean crust being made. And when that happened, it's pushing this island arc further and further to the left. The continental crust is getting pushed further and further to the right until the island arc ends up on top. It gets pushed up on top of the continent. All right. So ocean crust between the island arc and the continent. It's been subducting, it's been subducting, it's been subducting, and there's an island here, there's continent over here, and eventually that island arc is all the ocean crust is gone, and the island just runs right into the continent. The island arc and continent crust are both made out of intermediate and felsic rock, chemically. What will happen when intermediate and felsic rock collides with intermediate and felsic rock? What will happen at this point? Do intermediate and felsic rock have low or high density comparatively? They have low density compared to other things, right? Compared to mafic and ultramafic. The mantle rock is what chemistry? I should have asked that here. What chemistry is the mantle? Composition. Composition here is ultramafic. Ultramafic. Is ultramafic rock high density or low density? It's high density. All right, so we've got an island arc and a continent, low density, two low density things floating on top of mantle rock, which is high density. That means that when the island arc and the continent rocks collide, neither of them can push down into the mantle. It's like taking a ping pong ball and trying to push it under the water. It won't stay under the water. It's going to pop right back up to the surface. It's got too low of density to stay under the water. The continental crust and island arcs have too low of density to get pushed into the mantle. They can't. So instead of getting pushed down into the mantle, they're just going to get pushed into each other. When this happens, we call this accretion. accrete. To accrete is to stick something onto something else. So imagine this is all continent over here. Here's an island arc, and it comes and it's going to just accrete. It's going to stick onto the edge of the continent. They run into each other. They push one another up, actually. They make some really tall mountains. The mountains are built as island arcs are pushed into the continent, or other island arcs. Island arcs can actually do this to each other too. We've got two island arcs, they can collide, and that's how continents are made eventually. Do we get new igneous rock made in stage F? This is a little tricky. This is where I was talking about earlier, where we get movement, but we don't have heat added where the movement is happening. So for the most part, no, we're not going to make igneous rocks here. I don't care about a little bit. But really, I want you to just learn no. The answer is basically no. If you were a geologist, I'd have to explain more and explain why, yes, there are some igneous rocks here. But for the most part, we're not going to worry about igneous rocks being in stage F. Why do we not worry about igneous rocks in stage F? What's not happening here? We don't have heat added, so we don't have melting. Because we have no melting, we don't have magma. Because we don't have magma, we don't have igneous rocks being formed. All right, stage F. Where do we see stage F happening on the planet? Main location that we can see right now is the Caribbean islands. It's actually really hard to see, but it's happening. There's historically, California was, the entire state of California is made of island arcs that accreted themselves to the western side of the United States, which makes for some really cool rocks and geology. It's a cool place to do my internship, but that's not happening anymore. No more accretion of island arcs onto California. That's all done. So this is where it's happening. You can see this line of mountains in here. We had some island arcs come on here onto South America. We also have an island arc that's moving this direction, and it will eventually accrete onto the bottom part of North America. So you can see here, this line right here, we've got movement that direction, and we've got movement this direction. So the little islands of the Caribbean, it's Cuba, Haiti, and Puerto Rico, these will all become part of North and South America someday. It's hard to find these on Earth because island arcs are tiny, and geologically it does not take a lot of time for them to become accreted, so this is the best example we've got. I think this is a very good stopping point. I did a good guess that we would get through from A through stage F. So to review, see here, let's look at this. To review, we've got stage A, which is a stable craton, continental crust attached to oceanic crust, nothing geologically interesting happening. Stage B, we've got heat starting to come up from the mantle, from convection cycles that are starting in the mantle, and it's pulling, stretching apart the continent into two new pieces. We're going to get some volcanoes there. Yes, we get igneous rocks. In stage C, we're focused just on right there in the middle of that oceanic crust where we've got convection cells coming up. It's melting the asthenosphere, creating new magma, which is going to come up and create new ocean crust, which is an igneous rock. Yes, we have igneous rocks at stage C. Stage D, we are only focusing on the quiet, fully diverged, moved away from the other, from the rift and moved away from the other continent. We're focusing right there on the edge of this continent, on the full divergent margin. No heat added, nothing melting, no magma, no igneous rocks. Stage E, more and more oceanic crust is made. The oceanic crust goes under stress and eventually breaks and subducts. When it subducts, it's pushing itself into the hot mantle. The heat from the mantle is going to partially melt the oceanic crust and create magma. That magma will go up, go through the oceanic crust, create volcanoes, new igneous rocks, and a whole island made of igneous rocks. And stage F is where we're ending today, where the oceanic crust is running out, and then the island arc that was created gets stuck or accreted onto the continent. We don't care about igneous rocks in this stage because we don't have heat added in a significant way. There you go. What do I want you to do for your quizzes? I want you to each pick 2 of the stages and explain to me what is happening. Tell me the name of the stage. Tell me what is happening. Tell me where on Earth is this happening. And tell me, are igneous rocks being made? And if igneous rocks are being made, why do you know that they're being made? Or why do you know that they're not being made? Do that. That's one of your quizzes. So quiz 1 and 2, just each of you, when you get together, again, you need to agree. This is so important for the quizzes, you guys. You must agree with each other because I'm going to just give you all the same thing in there, mostly for a grade. And I'm sorry, I haven't come up with a good way to do this, but we're working towards completion, which means I just want to make sure you understand. So work with each other, help each other understand. If you don't agree, stop and start over again. So do all 6 stages. Each student choose 2 stages, go through the whole thing. You can use the drawings. You can draw on a whiteboard if that helps you. And then do the written quiz, where each of you write me an email and explain to me why does ocean crust go down so that there's water on top, and why is continental crust up high. And then I want you all together to remake the convection cycle plate tectonic answer from last week. I want you to redo that one. Make sure that you all agree. Make sure that you get the complete cycle in there, not just arrows going up somewhere and coming right back down in the same spot. Make sure you go through the whole cycle and tell me what's happening at each stage. You're doing well. I'm proud of you. Thank you for your patience, and I will get you another video next Sunday for Monday's class. All right. Bye.